Okay, thank you. I thought Aaron presented that beautifully. I have to say this paper really struck a nerve for me. I recently wrote a paper in which I used an instrument to establish some causal results, and to our surprise, we found that our IV estimates were like 3 or 4 times larger than our OLS estimates. And in the paper, we tied ourselves in knots trying to explain this big gap between OLS and IV. A conference discussant gave us a hard time about this gap. The whole experience was unsettling. Well, it turns out, everyone's struggling with the clicker today. But can we have a quick clicker tutorial here? What's the button I want to use here? Red. Okay, red to go forward. So it turns out my experience was not unique. Wei Jiang has this nice paper in which she surveyed more than 200 finance publications that use IVs, and she finds that on average, the IV estimate is 9 times bigger than the OLS estimate. More interesting, even when the logic in these papers explicitly says, we expect the IV to be smaller than the OLS estimate, they almost always find the opposite. You almost always find IV is bigger. And that's unsettling, hence this provocative title, have instrumental variables brought us closer to the truth? Wei's answer seems to be no. She writes, it's hard to argue that the IV estimates are closer to the true and unknown parameters than the OLS estimates are. In other words, maybe these problems with IV are just so big, maybe we're just better off with OLS. So Aaron's paper helps us understand these big gaps between OLS and IV estimates. In doing so, he helps us answer this question that Wei has raised. Given how popular instrumental variables are, not just in finance research, but in social sciences, I would say this is a very important paper. So again, how does this thing work? We have to start with capital J models. So this is important. I'm going to argue soon that J can't be too small. Like, I wanted to apply their approach to my recent paper. I only had 2 IV models in my paper. That's not enough J to really apply this. So that might limit where this can be applied. But in each model, little j, each model has its own y variable. But all the models share the same regressor, chi. And what we're trying to get here in each model is the causal elasticity beta from that model j. But we have these 2 problems. The first is we can't observe chi. We only have data on x. X equals chi plus measurement error. Now imagine you could run a hypothetical regression of x on chi. The r squared from that regression is this tau squared quantity. Tau squared, again, it's a measure of how good is our proxy for chi. The biggest you can get is 1. If your tau square is 1, you have a perfect proxy. The second problem is that chi is endogenous. Chi is correlated with this disturbance u. But let's suppose we have a perfect instrument. It's perfect in the sense that the instrument's unrelated to the model disturbance, u, as well as the measurement error, epsilon. Then we have well-known results from econometrics. The IV estimator converges to the truth, to beta j, but OLS doesn't. OLS converges to beta j multiplied by this tau squared thing. That's the well-known attenuation bias. The worse is our measurement error in chi, the more attenuation there is. And the second term there is gamma j. Again, that's the omitted variable bias in model J. That comes from the endogeneity of chi. So let's take those 2 estimators. I've written them again at the top. You'll notice they both depend on the truth, beta j. Let's substitute in that second equation into the first one, and then you get this beautiful relation here that relates an OLS estimator to an IV estimator. It kind of looks like a regression, and the paper's kind of big, clever ideas to actually interpret this as a meta-regression. Let's literally regress the OLS estimate on the beta estimate. Remember, this is a model in which we have capital J observations. The coefficient B delivers a measure of tau squared. The intercept delivers a measure of the average amount of omitted variable bias across these J models. So one note here is it's worth pointing out, what's identifying the meta-regression? Well, it's being identified off of variation in true beta across these models. So to make this work, the true causal elasticity has to be different in your various models. The second thing that's worth adding to the paper is that not only can you measure the average bias, you can measure the emitted variable bias in every single one of your models. It's just the estimated intercept plus the estimated residual. And that could be useful in some settings. Then there are some great extensions in the paper: instrumental validity, heterogeneous treatment effects. You can add controls. You can fix attenuation bias that comes from the fact that we have a noisy estimate of IV. I'm not going to focus on those extensions. I'm going to focus on the parts of the paper that I found most interesting. So let's apply this. I'm also going to focus on the Mian and Sufi example just so we see how it works. So to make this work, you open up Mian and Sufi, you go to their table 4, and in this table 4, we're seeing 12 versions of the same regression. In every single one of these regressions, the Y variable is employment growth at the county level, and in every regression, the X variable is change in housing net worth. What's different across these models is that we're estimating them in different subsamples. So we're estimating them in 6 different subsamples formed on establishment size. And then in panel A, we've got a bunch of OLS estimates of that model. In panel B, we have a bunch of IV estimates of the model. And Mian and Sufi say, the problem with OLS, positive emitted variable bias. They said, we expect the OLS coefficients to be too big. And sure enough, in 3 of the regressions, OLS is bigger than IV. But in the other 3, the opposite is happening. So it's weird that they're talking a lot about positive OVB, but not systematically finding it. What we end up with, though, are these 6 pairs of IV and OLS estimates. We can plot those 6 pairs in this type of graph, where again, on this axis, we have the IV estimate. In this axis, we have the OLS estimate. Those 6 dots correspond to those 6 pairs of estimates. And the meta regression just fits a line through those 6 data points. The slope of that line tells us about tau squared. We get a number way below 1, telling us that there's quite a big problem with proxy quality. And that's interesting because Mian and Sufi, they don't talk much about proxy quality, but it turns out that's a big source of the bias in OLS regressions. The intercept here tells us about the average level of emitted variable bias. It's a small positive number, so yeah, they posit that it's positive. It is positive, but it's quantitatively not a big deal. So we have now 2 numbers for this paper. We've got tau squared. We've got average emitted variable bias. So we can take those 2 numbers and place the Mian-Sufi paper in this nice chart. So what's going on here? Here we have the average emitted variable bias in the paper. Here we have the proxy quality in the paper. Great. There's Mian and Sufi. And now we can kind of compare these papers. It's a beautiful chart. But wait a second. We just ran a regression with 6 observations in it. How wide are the confidence intervals on these estimates? I'm curious, do the confidence intervals look nice and tight like this? Or do the confidence intervals look more like this? It's a potential concern, right? We're running a meta-regression with 6 data points in it. The paper doesn't have any confidence intervals. It doesn't have any standard errors. It should, and it easily could. So I'll give it a try. Let's get some confidence intervals. Since we're dealing with very small sample sizes, we should use something like Bootstrap to do that. So let's do it. So I'll start with the simplest Bootstrap. I'm just going to independently resample residuals from the meta-regression to get pseudo data, a pseudo data sample with 6 data points in it. So again, basically what I'm going to do here is I'm going to simulate the OLS coefficients by taking the estimated A, B, IV coefficient, and I'm just going to resample with replacement from the estimated residuals. With that pseudo data, I re-estimate that meta-regression in the pseudo data sample, which gives me a pseudo value of tau squared and the average bias. And I'm going to repeat those steps, thousands and thousands of times. That allows me to compute a confidence intervals around things like tilde, average OVB. And when I do that, here are the confidence intervals I get. They're a bit wide, but I'm actually really impressed how tight they are, given that we only have 6 data points here. One cool thing you can say is that of average omitted variable bias, it's not even significantly different from 0. But this has problems. I need to do a better bootstrap. The problem here is that we have to adjust those confidence intervals for the fact that we have sampling error in the IV estimates. This is the well-known problem of generated regressors. Remember that the X variable and the meta-regression are these 6 IV estimates, and each of those IV estimates comes with quite a lot of standard error. So we need to adjust the confidence intervals. We can do that by going into that table of Mian-Sufi, grab the standard errors for each beta IV, run the same bootstrap as before, but now the change is that I'm going to draw an IV coefficient from a normal distribution centered at the estimate where we're taking into account the standard error of each of those betas. And now we get this adjusted confidence intervals, which are now looking quite a bit wider. How wide is this OVB one? It's in units of beta. For comparison, these OLS betas range from like 0.02 to 0.434. So they are what they are. This is how we could get confidence intervals. But even this isn't perfect. There are a lot of further refinements that we should do to the bootstrap. The details are not interesting. It's all kind of mundane, straightforward stuff. My only point is I think it would make the paper even more useful if they tell us how to conduct inference. It's not too tough. But this made me think of one potential problem with the paper. In practice, when we do this, we're using betas estimated with error. Thank you. This raises a potential problem with correlations and measurement error, which produces its own omitted variable bias in the meta-regression. There may be a way to fix it. Let me conclude. Given how important IVs are, I think this is an important paper. It's very clever. I wish I had written it myself. My comments are really about finite sample issues. Add inference to the paper. Is there a potential bias from correlated measurement errors? Thank you.